Hi everyone! Ever wondered what makes plastics, some drugs, and even explosives possible? It all starts with hydrocarbons, and today we'll focus on two fascinating types, alkenes and alkynes. And in this presentation, we will tackle the overview on alkenes and alkynes and the various reactions that can happen to them. What are alkenes and alkynes? Alkenes are unsaturated hydrocarbons containing at least one carbon-carbon double bond, while alkynes are unsaturated hydrocarbons with at least one carbon-carbon triple bond. Alkenes and alkynes are types of unsaturated hydrocarbons that are more reactive than alkenes. The main difference is that alkenes have double bond, while alkynes have triple bond. In comparison to alkenes and alkynes are much more reactive. In fact, alkene serves as a starting point for the synthesis of many drugs, explosives, paints, plastics, and pesticides. Alkenes can undergo 5 major types of reactions. We have combustion reactions, addition reactions, elimination reactions, substitution reactions, and rearrangement reactions. These double and triple bonds make alkenes and alkynes more reactive than alkanes. They're used to create a variety of important products. Alkanes can undergo various reactions, which will be explained and elaborated in this discussion.
Most reactions that occur with alkenes are addition reactions. As the name implies, during an addition reaction, a compound is added to the molecule across the double bond. The result is the loss of double bond or alkene structure and the formation of the alkane structure. The reaction mechanism of a reaction describes how the electrons move between molecules to create a chemical reaction. In simple terms, addition reactions are all about breaking the strong bond, which is the double bond, and adding new atoms to make the molecules more stable. This is a key reaction type in organic chemistry, especially for converting unsaturated compounds like alkenes into more stable saturated compound. Imagine you have 2 carbon atoms holding hands very tightly, which is the double bond. They decided to let go a bit, break the double bond to invite 2 friends, which is the X and Y. To join them, X hold hands with one carbon and Y hold hands with the other. By the end, the 2 carbons are still connected but not as tightly with a single bond now. And they've made new connections with their friends X and Y. It's like the carbons are forming a new group of 4. There are 4 major types of addition reactions that can occur with alkenes and alkynes, which included hydrogenation, halogenation, hydrohalogenation, and hydration. First, what happens in hydrogenation? Imagine a double bond in a molecule. It's like a tight handshake between 2 atoms. Now, in a hydrogenation reaction, we break this double bond by introducing hydrogen gas or H2. This breaking allows the 2 hydrogen atoms to attach to the molecule, one on each side. The result, our previously unsaturated molecule becomes saturated. A quick memory tip: the word hydrogen in hydrogenation tells you what's being added, which is the hydrogen gas. So whenever you hear hydrogenation, just think of H2 jumping in and stabilizing the molecule. In the slide, you see a molecule with a double bond. This double bond is like 2 carbon atoms holding hands tightly, forming an unsaturated molecule. To start hydrogenation, introduce hydrogen gas. The process involves introducing hydrogen gas to the reaction. Step 2. Break the double bond. With the help of a catalyst, the double bond is broken. Think of it as the carbon atoms letting off their tight handshake. Step 3. Attach hydrogen atoms. The hydrogen molecules then attach to the carbon atoms, one hydrogen on each side. This turns the molecule from unsaturated to saturated, making it more stable and less reactive.
For the addition reaction type called halogenation, the group 7A elements or the halogens are added across the double bond. The most common halogens that are incorporated include chlorine, bromine, and iodine. Notice that the term halogen is found in this reaction meaning making it easier to remember and recognize it. In simpler term, halogenation is the addition of a halogen to an alkene. So here we have an example, ethane and chlorines. So the double bond in this ethane is going to be removed, and the halogen chlorine is going to bond with these two carbons. The process of halogenation is going to be breaking of the double bond, and then add the halogens, and there you will have it, a single bond, and each of the halogen chlorine bonded to the two carbons that were touching the double bond. So that's the process of halogenation. In hydrohalogenation, alkenes react with molecules that contain one hydrogen and one halogen, hence the name hydrohalogenation. HCl and HBr are common hydrohalogens seen in this reaction type. In hydrohalogenation, the halogen is a polar molecule, unlike the non-polar molecules observed in the halogenation and hydrogenation reactions. In the case of the hydrohalogen, the end of the molecule containing hydrogen is partially positive, while the end of the molecule containing the halogen is partially negative. When the negatively charged electron from the alkene double bond attacks the hydrohalogen, it will preferentially attack the hydrogen side of the molecule, since the electron will be attracted to the partial positive charge. The halogen will then form the negatively charged anion observed in the intermediate structure and attach second during the addition reaction. And then the final product is a haloalkene. So we have an example here, an ethane and a hydrochlorine, or the HCl. So the double bond of this alkene is going to be broken, and then one of the carbons from the broken double bond grabs the hydrogen from the HCl, and the other carbon from the double broken bond will grab the chlorine from the HCl. So then we will end up with a molecule where the once double bonded carbon are now going to be single bonded to each other. So one of these carbon has now a new hydrogen atom attached to it, and the other carbon has now a chlorine atom attached. So that's the process of hydrohalogenation.
Today, I'll be discussing an important type of addition reaction, which is hydration. Just like when you are feeling thirsty, the terms hydration and dehydration refer to water. Hydration means the addition of water to a molecule, just like when you feel fully hydrated or full of water, while dehydration means the removal or elimination of water, just as when you are feeling dehydrated and need some water to drink. Similar to the hydrohalogenation reaction, water is also a polar molecule. Have you ever felt really thirsty and needed to drink water? Just because your body needs hydration. In chemistry, hydration refers to the addition of water to a molecule. This process is important in many chemical reactions, especially in organic chemistry and industrial processes. Hydration is the opposite of dehydration, which means the removal of water, just like how our bodies lose water and we feel dehydrated. Molecules can also lose water in dehydration reactions. One common example of hydration is in the conversion of alkenes to alcohols. When water is added to an alkene in the presence of an acid catalyst, it forms an alcohol. This is useful in many industries, including the production of beverages and pharmaceuticals. Additionally, just like in hydrohalogenation reactions, where hydrogen halides add to molecules, water is also a polar molecule, meaning it has both positive and negative charges, making it essential in chemical reactions.
Let's proceed to the next slide. This reaction involves the addition of water to an alkene, resulting in the formation of an alcohol. To help you visualize this process, let's look at this reaction mechanism.
In hydration, water or H2O is split into two components. The first one is H positive means hydrogen ion. The second is OH negative means hydroxyl group. These components are then added across the double band of an alkene in the following steps. The step 1 is protonation or adding H positive. The double band in the alkene attracts a hydrogen ion or H positive from the water molecule. This results in the formation of a carbocation, which is a positively charged carbon atom. Refer to the first part of the diagram where the double band is breaking and a positive charge is forming of one carbon. The step 2 is nucleophilic attack or adding OH negative. The negatively charged hydroxyl group or OH negative is attracted to the positively charged carbocation. The OH group attaches to the carbon, completing the reaction. In the diagram, you can see how OH negative is added the carbocation, leading to the formation of an alcohol. Next, the step 3 is formation of the final product. After both H and OH are added, the result is an alcohol, a compound with an OH negative functional group. This process is similar to hydrohalogenation except that instead of adding a hydrogen halide like HCl, we are adding H2O, means water. In industry, hydration is used in the production of ethanol and other alcohols, which are essential for fuels, cosmetics, and pharmaceuticals. In biology, this reaction occurs in biochemical pathways, helping in energy production and metabolism. In summary, hydration is an addition reaction where water is added to an alkene to form an alcohol. By the following steps of protonation, carbocation formation, and nucleophilic attack, we can understand how this process works. This reaction is widely used in industries and even plays a role in biological system. So next is let's proceed to the Markovnikov's rules. In more complex molecules, hydrohalogenation and hydration reactions can lead the formation of more than one possible product. For example, if 2-methylpropene reacts with water to form the alcohol, two possible products can form as shown below. However, the addition reaction is not random. One of the products is the major product, being produced in higher abundance, while the other product is the minor product. So I'll be discussing about these rules to determine the major and minor products in this reaction. When dealing with more complex molecules such as 2-methylpropene, adding a molecule like water or hydrogen halides can lead to more than one possible product. However, the reaction does not occur randomly. Instead, the Markovnikov's rules helps us predict which product will form in greater abundance. Markovnikov's rule states that when an asymmetrical reagent like H2O or HCl adds to an asymmetric alkene, the hydrogen H positive attaches to the carbon with more hydrogen atoms, while the other part attaches to the carbon with fewer hydrogen atoms. So the step 1 is protonation or adding H positive. The hydrogen ion H positive from H2O or HCl attaches to the carbon in the double band that already has more hydrogen atoms. So the step 2 is carbocation formation. This creates a carbocation intermediate at the other carbon. A more stable carbocation leads to the major product. The step 3 is nucleophilic attack or adding OH negative or X negative. The negatively charged group, the OH negative from water is hydration or from hydrohalogenation, attaches to the carbon with fewer hydrogen atoms, forming the final product. Example of hydration of 2-methylpropane. Let's take 2-methylpropane reacting with water. Two possible alcohols can form. According to Markovnikov's rule, the negative OH group attaches to the more substitute carbon, the one with fewer hydrogen atoms, leading to a major product. The other possible product is where the OH negative group attaches to the carbon with more hydrogens, is the minor product. The same rule applies in hydrohalogenation, where HCl or HBr adds to an alkene, forming a major and minor product.
Next is, in these types of reactions, Markovnikov's rule can be used to predict which product will be the major product. Markovnikov's rule states that in addition reactions with HX, where X is a halogen or the OH group from water, the H always attaches to the carbon that already has the most hydrogens, and the X attaches the carbon with the fewer hydrogen atoms. This occurs because the carbocation intermediate that forms as the reaction proceeds is more stable when it is bonded to other carbon atoms than when it is bonded with hydrogen atoms. In organic chemistry, addition reactions play a crucial role in transforming unsaturated hydrocarbons into more complex compounds. These reactions involve adding atoms or functional groups across a double band, characteristic features of alkenes. However, in cases where the reacting molecule is asymmetrical, such as in hydration and adding H2O, or hydrohalogenation adding HX, more than one possible product can form. This is where Markovnikov's rules becomes essential, as it predicts which product will be the major product in such reactions. Markovnikov's rule states that in an addition reaction involving HX, where is a halogen or an OH group from water,
The hydrogen will attach to the carbon that already has more hydrogen atoms, while the X group will attach to the carbon fewer hydrogen atoms. This pattern occurs due to the stability of the carbocation intermediate, which is formed during the reaction. To understand why this happens, because we need to consider carbocation stability. In organic chemistry, tertiary carbocations are the most stable, followed by secondary and also the primary carbocations. The reactions naturally favors the formation of the most stable carbocation, which is typically found at the carbon that is bonded to more carbon atoms rather than hydrogen atoms. Because of this, the addition of HX follows a specific pattern, ensuring that the more stable product is formed in major product, while the less stable product is formed in smaller amounts, the minor product. For example, in the hydration of 2-methylpropane is water, H2O is added to the double bond. According to Markovnikov's rules, the H positive from water attaches to the carbon that already has more hydrogen atoms, leading to the formation of a more stable carbocation intermediate. The OH negative is grouped from water then bonds to the carbocation, resulting in the major product, which is more stable alcohol. Meanwhile, an alternative less favorable pathway produces the minor product but in much lower quantities. The same concept applies to hydrohalogenation reactions, where HX such as HCl or HBr reacts with an alkene. The H positive attaches to the carbon with more hydrogen atoms, while the X negative is bound to the more substitute carbon, ensuring formation of the major product. Markovnikov's rule is significant in industrial and pharmaceutical chemistry. It plays a vital role in alcohol production, polymer synthesis, and drug manufacturing, ensuring that reactions occur efficiently and predictability. By understanding how Markovnikov's rule governs these addition reactions, chemists can manipulate reaction to synthesize desired compound more effectively. That's all.
In an elimination reaction, a molecule loses a functional group, typically a halogen or an alcohol group, and a hydrogen atom from two adjacent carbon atoms to create an alkene structure. Elimination reactions are essentially the reverse reaction of the hydrogen and halogenation addition reactions. Elimination reactions can also occur with the removal of water from alcohol.
To sum up, an elimination reaction is a type of a reaction in which two substituents are removed from a molecule in either one or two-step mechanism. The one-step mechanism that we're talking about is the E2 reaction, which is a bimolecular, and a single-step elimination with a single transition state. E1, on the other hand, is the two-step process of elimination, the ionization and deprotonation. In ionization, the carbon-halogen bond breaks to give a carbonate intermediate, and the deprotonation of the carbonation occurs. E1 elimination happens with highly substituted alkyl halides that are bulky, limiting their room for E2 mechanisms. So we have an example here on the left side, which is the reactant. The starting compound is ethanol CH3CH2OH. Under suitable conditions, elimination process occurs. usually heat and an acid catalyst like sulfuric acid. Ethanol undergoes an elimination reaction where a water molecule H2O is removed, and then the removal of negative OH from one carbon and H form an adjacent carbon leads to the formation of a double bond carbon. The resulting product, which is the ethane on the right side, C2H4, an alkene, and water, and down below H2O there is formed as a side product.
So I have here a picture, a drawing I made myself to further understand the E1 and E2. So this person's right here is represent the carbon. Alright, carbon. And here represents the single bond. And the cup here he's holding is the leaving group. Leaving group. Alright, here is the hydrogen. So, in E1, a carbonation forms and a hydrogen is stolen from a neighboring carbon. Then the remaining electrons make another bond, which is the holding hands. In E1, the leaving groups then leaves. So, mawala na siya. Mawala na siyang sikap. Nagigunitan ni leave na siya. Leaving na. Leaving. Yes. Carbons sila. And they were holding hands. Unja, and this in the right side man sa laki no is nawala na. Wala na siya kay ni-leave naman siya. So, isa na lang din na nag-hold sila sa kakap. So, in E2, the leaving group and hydrogen leave at the same time. So, naman na siya single bond. Si hydrogen, nawala naman si leaving group. Si hydrogen in E2 plus mechanism. Mawala po na si hydrogen. Bigaan naman na kanila. Mainighawa niya si kawato na si hydrogen ni nucleophile. Kawato ni nucleophile si hydrogen nga gigunitan aning baje. Ano? And that is when the double bond forms from leftover electrons. So there na guys, nawala naman si hydrogen hasta tong leaving group inilibs naman. Sila na lang. Nawala na ilang kape. So naana sila time nag-hold sila o nag-hold hands. Yay! Single band na sila. Double band na sila guys. May na siya. Double band. So bye guys.
Good day! Today we're going to explore the differences between the alkenes and the alkynes and their rearrangement reactions. And as we all know that alkene has only one double bond, while the alkyne has a triple bond. These compounds are essential in industrial chemistry, pharmaceuticals, and material science. There are also differences between the alkenes and alkynes. For the alkenes, it is used for plastics or polyethylene solvents and drug synthesis, while the alkynes, it is used for welding, or the acetylene, organic synthesis, and pharmaceuticals. Rearrangement reactions involve molecular restructuring for stability. And an example for the reaction for alkene is hydride shift. And for an example for the alkynes is partial hydrogenation. So those are the two rearrangement reactions, the hydride shift for alkenes and the partial hydrogenation for alkynes. Alkenes and alkynes are vital or play a vital role in the chemistry, community, and industry. Understanding their transformation helps advance materials and medicine. And that's all for rearrangement reactions.
Due to the high reactivity of alkenes, they usually undergo addition reactions rather than substitution reactions. The exception is the benzene ring. The double bonded structure of the benzene ring gives this molecule a resonance structure such that all of the carbon atoms in the ring share continually rotating partial bond structures. So, alkenes and alkynes primarily undergo addition reactions due to the presence of their double and triple bonds. However, substitution reactions is rare. The benzene ring structure is stabilized by resonance. One of the few reactions that benzene rings will undergo are substitution reactions. Benzene is stabilized by resonance, which means its electrons are delocalized across the entire ring, unlike alkynes and alkenes, where electrons are localized in double or triple bonds. Benzene has a continuous overlap of p orbitals, forming a conjugated system. Thus, the overall structure is very stable compared to other alkenes, and benzene rings do not readily undergo addition reactions. They behave more similarly to alkane structure and lack chemical reactivity. One of the few types of reaction that a benzene ring will undergo is substitution reaction, in which an atom or group of atoms is replaced by another atom or group of atoms. Halogenation is a common substitution reaction that occurs with benzene ring structures. Benzene is very stable, so it does not easily react like other compounds. Instead of adding atoms, it swaps one atom for another in a substitution reaction. In substitution reaction, one atom in a molecule is swapped for another. So as you can see sa picture below, the hydrogen atom is replaced by one of the fluorine atoms. So the result is, it's like trading one thing for another while keeping the rest the same. Because as you can see, the hydrogen atom kay replaced by the fluorine atom, pero ang the rest is remain the same. So mao na siya substitution reaction.
Combustion reactions happen when hydrocarbons react with oxygen in the air to produce carbon dioxide and water. This is a type of exothermic reaction, meaning it releases energy in the form of heat and light, which is why combustion reactions are commonly associated with fire or burning. However, we have to consider that it has two types, which are the complete and incomplete combustion reactions. So, for a typical reaction formula of a complete combustion reaction, it involves hydrocarbon reacting with oxygen, resulting in the formation of carbon dioxide, water, and heat. So, another reaction that alkenes and alkynes undergo is combustion reaction. Mo involved ni siya of reaction between a fuel, typically a hydrocarbon, with oxygen, forming carbon dioxide and water. Sige, for instance, ang mo-react nga hydrocarbon, which is made of hydrogen and carbon atoms, will react with oxygen. And the carbon will combine with the oxygen, therefore forming carbon dioxide, while the hydrogen combines with the oxygen to form H2O or water. So maong carbon dioxide and water are the products of combustion. And since this process is an exothermic man na process, meaning mo release ni siyang energy nga mo manifest as heat and light, nga mao ang hallmarks sa combustion. Therefore, ma-associate nato ang combustion with fire or something that is burning. Complete combustion occurs when fuel burns completely with sufficient oxygen, producing carbon dioxide and water. On the other hand, incomplete combustion happens when fuel burns partially due to insufficient oxygen, producing carbon monoxide and soot, which are fine particles of elemental carbon. Therefore, the primary factor in combustion reactions is the availability of oxygen. So sa giisgutan kanina, there are two types of combustion, which are the complete and incomplete combustion reactions. So the first one, which is complete combustion, mahitabo ni siya if there is a sufficient supply of oxygen, which means nga all or tanan of the carbon atoms will react completely with all of the oxygen molecules to form carbon dioxide. However, if dili sufficient ang supply sa oxygen or naay other factors nga naka-affect sa combustion process, it will result to incomplete combustion, which is the second type of combustion reaction. And it will instead produce carbon monoxide and soot instead of carbon dioxide and water. So, kining soot, this is just unburned carbon particles nga ni-congregate or nibuo together into a mass. Since dili man sufficient ang oxygen, dili punta ng carbon atoms ang mo-react. Therefore, kining mga unburned nga carbon atoms or molecules mo form into soot nga atong makita as the black substance in ignite fire. And for some trivia, the typical fire nga atong makita or gamiton, the orange-yellow flame, is an example of incomplete combustion. Muna siyang mo-exhibit ni siyang orange-yellow flame. However, ang fire nga makita nato sa mga gas stoves exhibits complete combustion. Mao nang iyang color is blue. Because since complete combustion man na siya, efficiently na use up ang tanang carbon atoms due to the abundance of oxygen. So, mo-react ang tanang carbon atoms with oxygen molecules, which means makaproduce siya of very hot flames and light because of its purity. Makonsider man siya nga pure fuel. So, ang specific na wavelength sa light nga na-produce niya will fall under the blue spectrum, causing us to see its beautiful blue glow of the flame. So, there are the formulas for the complete combustion reactions for alkenes, alkanes, and alkynes. This is just a brief comparison for the similarities and differences between the three. However, we'll focus on the alkenes and alkynes. Now, here's an example for the combustion reaction of an alkene, which an example here is ethene, also known as ethylene, which is a colorless, flammable, gaseous, unsaturated hydrocarbon found in coal gas. So, we will follow the formula for an alkane indicated on the slide before, which is CnH2n plus 3n divided by 2 for oxygen, which results into NCO2 plus NH2O. To find the N in the formula, we just have to find out the number of carbons in the hydrocarbon and then simply plug the value into the formula. Since the formula for ethene is C2H4, it has 2 carbons. Therefore, just plug the 2 carbon value into the formula for N. Therefore, if you calculate, the complete combustion reaction equation for ethene is C2H4 plus 3O2 results into 2CO2 plus 2H2O. The number of atoms and molecules on each side are completely equal. Next, we have for the alkynes. They are just very similar to alkenes, however, with some slight differences. The example here is ethine, another colorless, gaseous hydrocarbon used chiefly in organic synthesis and as a fuel, which ato nang natakil nga hydrocarbons are excellent fuels. Just like for an alkene, we will just follow its respective formula, which is CnH2n minus 2 plus 3n minus 1 over 2 for oxygen, resulting into NCO2 plus n minus 1 H2O. Then plug the number of carbon atoms, which is 2, into the formula, and you will have the complete equation. Pero instead of 1 molecule of ethine, nga namang 2 molecules man ang needed to form this complete reaction based on the equation. It's because the balanced equation requires 2 molecules of ethine to react completely with 5 oxygen molecules in order to produce 4 carbon dioxide molecules and 2 water molecules. If usara ang gamiton nga ethine molecule, the reaction will be incomplete. Therefore, the complete balanced combustion reaction for ethine is 2C2H2 plus 5O2 forming 4CO2 plus 2H2O. So, moto siya ang complete reaction for ethine. And that is the combustion reactions for alkenes and alkynes.
For the summary, alkanes are unsaturated hydrocarbons containing at least 1 carbon-carbon double bond, while alkynes are unsaturated hydrocarbons with at least 1 carbon-carbon triple bond. Alkanes and alkynes can undergo 5 major types of reactions, which are addition reactions, elimination reactions, rearrangement reactions, substitution reactions, and combustion reactions. Addition reacts are when a compound is added to a molecule across the double bond. The result is the loss of a double bond or alkene structure and the formation of the alkyne structure. There are four major types of addition reactions that can occur with alkanes and alkynes, which includes hydrogenation, halogenation, hydrohalogenation, and hydration. Elimination reactions are the reverse of addition reactions, in which a molecule loses a functional group, typically a halogen or alcohol group, and a hydrogen atom from two adjacent carbon atoms to create an alkane structure. It can also occur when the removal of water from alcohol. An arrangement reaction is a specific organic reaction that causes the alteration of the structure to form an isomer. A substitution reaction occurs when an atom or group of atoms is replaced by another atom or group of atoms. It is common in benzene rings because it allows the molecule to maintain its aromatic stability by replacing a hydrogen atom with another group. Combustion reactions happen when hydrocarbons react with oxygen in the air to produce carbon dioxide and water. This is a type of exothermic reaction, meaning it releases energy in the form of heat and light. And that's a wrap. We've reached the end of our journey together. We trust that this presentation has enriched your understanding of our topic. Farewell, and may your knowledge continue to grow. See you later, alligator!